All right, so it's pleasure to to welcome Tanmay virtually. I would have preferred to welcome him in person, obviously, but we'll have to settle for this for the moment. Tanmay is a very creative, versatile physicist with interest in all kinds of things, classical quantum physics, cosmology, general relativity, quantum field theory, model building, you name it. Okay, he has done a lot of extremely interesting work in these disciplines. I have learned a lot about his stuff from actually reading his incisive papers back in the day, and I continue to read them, and I'm obviously hoping that we are all going to enjoy the talk, and I'm pretty sure that we will. Just as a bit of history, Tanmay has been a PhD student, I think at Tufts with Alex Vilenkin.
That's correct. Yeah.
And then he has done several postdocs, I think, in Delaware. He was Joe Biden's postdoc, right? In case you didn't know. And Cambridge. And then I think you were a junior faculty at Tufts, right?
Yes, that's true.
And then he moved to Case Western and most recently to Arizona State. And he will tell us about unexciting physics today.
All right. Well, thanks a lot, Nemanja. Thanks for the invitation. As you can see, this background is very unexciting. Let me, okay, so this is I've been interested in this particle production in sort of some classical backgrounds, time dependent or inhomogeneous. And that's how I came upon this topic of sort of unexciting classical backgrounds. And so as for an introduction, so there are lots of situations where you would be interested in particle production. And if you recall, Hawking radiation was derived as particle production during gravitational collapse. And you can think of it as the time dependence of the gravitational collapse leading to pair production. Of course, in earlier processes, Schwinger pair creation, where you have an electric field, and the Schwinger famously calculated that the electric field would pair produce electrons and positrons. And of course, it's a famous result that the pair creation rate goes as e to the minus m squared by e type exponent. But if you look up Birrell and Davies, and there's quantum fields in classical sort of spacetimes, and there's a whole book on that. And so there are lots of examples where people look at pair creation in time-dependent backgrounds. And this particle production implies some sort of quantum instability of the classical background. And so, for example, black holes evaporate. And if you have a capacitor, then the capacitor will discharge. Or if you have the inflaton rolling down its potential, then it will produce particles and the universe will reheat. And so it's a sort of a very general problem. So I was interested in the question if there are backgrounds that are protected from such dissipation, in which you have some non-trivial time dependence, and yet there is no particle production. And I will get to my sort of personal motivation in just a minute. And I think it can be an important question. So let's just think of Schwinger pair production in QED. There is an electric field, and you produce electron-positron pairs. And this is the sort of Schwinger result over here, that the rate of particle production goes as this famous exponential. And the usual way of thinking about this is as a tunneling process, where these electron-positron pairs, they tunnel out of the vacuum. And I think that's the sort of dominant viewpoint. But it's actually, you can think of it as a time-dependent background as well by going to temporal gauge. Then this electric field is given by a gauge potential, which looks like E times T. And now you're doing quantum field theory in this time-dependent background, and you can calculate these electron-positron production rate. So that's a completely equivalent way of thinking about the problem. So some time ago, maybe a few months ago, actually, or maybe during these COVID times, our postdoc here, Carlos Cardona, and I started thinking about Schwinger pair production in non-Abelian gauge theories. So there you can think of an electric field in some gauge component, so E3. And then there's a coupling between all the different gauge colors. So you might start producing a W plus and W minus particles. So then an electric field configuration of a non-Abelian in a non-Abelian gauge theory would slowly decay due to pair production. And so that sort of got me thinking that, and I'm not a QCD person, so I don't, well, anyway, let me just say that normally we think of in QCD, there are these electric flux tubes. And if there are electric flux tubes and there's some electric field, you would think there'd be Schwinger pair production in those electric fields, and those flux tubes would decay. So can it be that you have some non-Abelian electric field configurations which actually do not lead to Schwinger pair production and are somehow saved or protected from this dissipation? So that was the kind of question that came to me. And of course, there's been lots of work on this kind of Schwinger pair production in these non-Abelian gauge theories. And I think maybe Carlos and I were the first to think about this in this time-dependent way, and our results actually differ a bit from the others, but I won't get into that over here. All right, so this is a problem. And so it turns out that there was another example which is similar in spirit. This is in QED in 1+1 dimensions. And my student from a long time ago, Yizhen Chu, who Nemanja might remember, he and I had looked at some time ago. So this is massless QED in 1+1 dimensions. So here's a Lagrangian, there's a fermion, and it's coupled to a gauge field. So it's a simple model. And you can consider putting external charges in this 1+1 dimension. So you have a plus Q and a minus Q. No, can you see my arrow over here? My pointer? Yeah, okay. So this is like a capacitor in 1+1 dimension. And so classically you would think there's some electric field. And of course, if you start producing particles, then this electric field will decay. So this model is simple enough that you can bosonize and then think of these this current psi bar gamma psi in terms of a scalar field. And then you have a bosonized Lagrangian over here. And so it's a scalar field coupled to the electric field. And when you solve this problem, so this can be solved completely, and you start with this electric field in this capacitor, and then you find that the electric field decays, but it doesn't decay to zero. it decays into something that can be written down. I mean, so there's this theta functions in the first line. Those are the original electric fields, but then you have this extra piece over here. And this extra function f has a certain form. It has an exponential decay. And on this sketch, I have drawn the electric field as it looks like in the final state. So here you started with the capacitor decayed, and eventually you got an electric field. And after that, the Schwinger pair production stopped. So I would say that this final configuration is like is an unexciting electric field. And so this was one example where you set up a capacitor. If you choose this electric field, then that's not decaying anymore.
Question?
Yeah, sorry.
Question. I mean, that are you saying that so if you had just classically drawn that field configuration, it wouldn't be a solution of the equation of motion. But you're saying that when you combine it with pair production, it is actually a stationary state.
Yeah.
And particles are streaming out, or what's going on with the particles that are being created?
So I probably should have written it here, but the phi field is not trivial. It also condenses. So there's a condensate of this phi field, which is also static actually. And there's an electric field and scalar field configuration, which is just sitting there.
Do you have a picture in terms of the fermions? Is there a physical picture in terms of
the fermions? No, I don't have a picture in terms of the fermions.
Mm-hmm. Yeah. Okay.
So as with all sort of quantum field theory problems, you start with a simple harmonic oscillator. And so the question is, if I have a simple harmonic oscillator and I change its frequency in some way, in some externally controlled. So I'm not solving for any equations that have to do with omega, but I just assume that there's some functional form. And if I shake this simple harmonic oscillator, are particles created. So you work with the usual ladder operators, except that now omega is a time-dependent function. Okay, so here are A and A dagger. And so this is what we call the classical quantum correspondence for the simple harmonic oscillator. It's been known for a while, but I think so this is what we've been using, and we've kind of extended it to quantum field theory as well. So anyway, so here are the Heisenberg equations. Then you can solve this Heisenberg equation in terms of this pz star minus im omega z star. So that's z, this new variable z. You can write the solution in this way. And basically, these are Bogoliubov coefficients, which everyone knows about. But the interesting thing is that this z variable, this z of t, obeys the classical equation of motion. So, and z is complex. So if you were to solve this classical equation of motion with these initial conditions, then you have a solution to the quantum problem as well. So in a way, so what I'm saying is that you solve the simple harmonic oscillator in 2 dimensions, and you get the classical simple harmonic oscillator in 2 dimensions, and you get a solution to the quantum simple harmonic oscillator in 1 dimension. So this solves the sort of simple harmonic oscillator problem, and sort of in pictures we're shaking omega, the wave function maybe starts in a ground state and then gets excited. So this is the quantum picture. And the classical picture is that there's a ball rolling on a two-dimensional parabolic potential. And it has some dynamics. And the dynamics of this ball translates into the dynamics, the quantum dynamics. Anyway, so this you can do for any omega of t. And then if you want to find some expectation values or something, you can write them all in terms of z. You can write all quantum operators in terms of this classical variable. Okay. The initial conditions are basically that you start in the ground state. So the energy of the classical oscillator has to be omega by 2. And but you also have to give it some angular momentum. And as this omega is changing with time, the energy can increase. The energy has an expression like this. Of course, while the angular momentum stays fixed. So this is the basic dynamics of this simple harmonic oscillator. And now if you ask, are there unexciting simple harmonic oscillator backgrounds? What you want is that the energy at the final time should be 0. So you have to have this expression equal to 0 only at the final time. So at the moment, I don't care about what happens at intermediate times, but at the final time, I say that the energy should be 0. So can we find an omega such that the final energy is 0? And a solution can be obtained in a kind of simple way. If you write z to be the magnitude times the phase, the angular momentum constraint just relates the phase to rho, and the equation of motion gives an equation for rho. But now you can think of this equation as an equation for omega squared. So omega squared is 1 by 4 rho to the 4 minus rho double prime by rho. So you have this omega squared. Now the energy, if you write it in terms of rho and the phase, then you can eventually bring it to this form. The first is the radial kinetic energy, and this is the angular part. And if you want the final energy to be 0, then all that you require is that rho prime at the final time be 0, and actually rho double prime, which is rho double dot, same thing, should be 0, because then if rho double prime is 0, then if you go back over here, then you see that omega is 1 by 2 rho squared. And so the angular part will also be 0. So the way to get the 0 energy is to use this formula, omega squared is equal to this in terms of rho, and just choose a function such that rho prime at the final time is 0 and rho double prime at the final time is 0. So this is the solution. Omega is square root of any function you want, rho, provided it satisfies certain endpoint conditions. Of course, you would want omega to be real as well, so you have to make sure that this is a positive quantity. Anyway, just to give you an example, if I take rho to be 1 plus half tan hyperbolic of time, then omega turns out to be something like this. It does something, but in the initial and final stages, it is a different constants. And the energy grows at first, but then gets absorbed, and you're left with nothing. So this would be what I would call an unexciting simple harmonic oscillator. Of course, it's not that nothing happens. The phase of the wave function changes. And in this particular case, you can write down the wave function explicitly, and you can calculate the shift in the phase of the wave function. Okay, I think that's it for the simple harmonic oscillator. So now let me go on to field theory. So you can do the same kind of thing with ladder operators in field theory. Now the complication is that the variable little z becomes a matrix variable, a complex matrix Zij. And but the equation of motion is the same. It's capital Z double prime plus omega squared z is 0. But now this frequency, of course, is something like k squared plus m squared, k squared plus the interaction part. So it's really minus gradient squared plus some interaction matrix. And sort of you can go step by step. It's very similar to the simple harmonic oscillator. There are some initial conditions which are given by the initial value of omega. And these are all matrices, so it's a little more complicated. But in principle, the idea is the same. So just like we had the angular momentum constraint for the simple harmonic oscillator, here we have a few more constraints. This first one is the angular momentum condition. And the second one is sort of a reality condition. The energy, it turns out, is just trace of z prime minus I omega z whole squared. So that formula is also very similar to the simple harmonic oscillator case. So the first step is to think about some homogeneous backgrounds. So there's only time dependence. So you have a uniform electric field, for example. Then, of course, you can diagonalize the spatial part. So you can think about mode functions. And then you have a simple harmonic oscillator per mode. So you have z double prime plus omega squared z 0. And once again, you could think of it as an equation for omega k squared and write such an expression. And you could choose rho k as you wish, provided it satisfies certain boundary conditions. And this would be an unexciting background. However, there's a difficulty here. Omega k squared is minus k squared plus the interaction, but the interaction should not, is homogeneous. It's taken to be homogeneous, so it should not depend on k. And then, because of this, it turns out that homogeneous backgrounds can be chosen for a particular, so that any k mode is not excited, but it's impossible to get none of the modes excited. So there'll always be some modes that are excited. To see this, I'll give an example. Let's say you have an interaction like lambda phi squared of t, and then this is the quantum field psi squared. So you can take a certain mode, k equal to k star mode, and you can find omega squared. You can choose your rho k star such that the k star mode is not excited. But having done that, that fixes this lambda phi squared, because omega k squared is also k squared plus m squared plus lambda phi squared. So now you know what the background is. It's lambda phi squared is equal to this expression on the right. Now you can consider a different mode, say k equal to p, and then for that to be unexciting, you'd have to satisfy this equation. You'd have to satisfy this equation, that's the equation of motion, and then the boundary condition would say that the ZP should satisfy certain conditions at the initial time and the final time, which basically says that rho prime, well, we know rho initially, it's in its ground state. We know rho dot, which is initially, because that comes out from this classical quantum correspondence, so that should be 0. And then you have these conditions for unexciting background, which is rho prime is 0 and rho double prime is 0. But now you have to satisfy these 4 conditions on one function. And so it's, in general, it's too many boundary conditions to satisfy. And so in general, you will, this other mode that you were considering, k equal to p, would be excited. So, so I don't think you can have unexciting backgrounds for all modes, but you can choose your mode. Okay. But we don't stop there, because ultimately, if we have to start thinking about flux tubes, then we'd like to think about inhomogeneous backgrounds, which are time dependent. But this formalism of this classical quantum correspondence can be applied even for inhomogeneous backgrounds. And then again, here are the equations of motion. These are the constraint equations. And now I don't have the luxury of being able to diagonalize these matrices. And so I defined rho squared to be ZZ dagger. So rho squared is like the modulus of the Z. Then I can write Z is rho times U, where U is a unitary matrix. And then I can first try solving these constraint equations. And I get 2 conditions, that rho must commute with rho prime, and rho squared must anti-commute, well, anti-commute to give you I with this U prime U dagger. So anyway, a solution is U prime U dagger goes as 1 by rho squared. And once again, with this solution of the constraints, you can find that omega squared, this matrix omega squared, has to take the same form as for the simple harmonic oscillator. And the conditions on rho are that rho and rho dot, or rho and rho prime should commute, and you have all these endpoint conditions. So in principle, all the sort of the simple harmonic oscillator formalism carries through even to the case of inhomogeneous backgrounds. And as an explicit example, you could take something very similar to what we considered. Rho is some matrix A plus half tan hyperbolic T and some matrix B. As long as A and B commute, then this will give you an unexciting background. However, while this is a formal solution, I don't think it really solves the problem. The reason is that here we get, sorry, let me go back. So we get some omega squared, but there are further restrictions on omega squared coming from what kind of interactions we are considering. It depends on the physical system under consideration. So let me give you an example. So let's say omega squared is this expression on the right. And again, let's take this lambda by 2 phi squared psi squared interaction. Then omega squared is this Laplacian plus the mass term plus this interaction term. And then I can plug this back in to the boxed equation, and I can get lambda phi squared is something that depends on rho. But this phi squared is proportional to the identity matrix. And so remember, rho is a matrix. So rho is a matrix. And so I have to choose a matrix which satisfies all the conditions that I listed before. And for this particular system, for this lambda phi squared psi squared type of system, this thing on the right should be diagonal. And I thought quite hard of how I might arrange this, but I was unable to come up with such a matrix. And so that is still kind of an open question, that that you can find these unexciting backgrounds, but under what conditions are they suitable for the system of interest? There's another question, which is that whether you can have backgrounds that are unexciting for all times. Remember, in the earlier examples, particles were produced and then absorbed. And so in the end, the system was not excited, but you might require something stronger, that that there is no particle production at any time. That's a more restrictive problem, and it's in some ways it's simpler. So again, the energy is this trace of z prime minus I omega z whole squared. If you want E to be 0 at all times, then of course z prime has to be I omega z. Then you can differentiate this and you get this equation. And then you know that the left-hand side is 0 from the equation of motion. So you're left with omega prime z is 0. If z is invertible, then omega prime has to be 0. And you're left with a trivial background. So if you're thinking about unexciting for all times, this would seem to say that that the only background is a trivial background. However, there are examples which kind of beat this. One is the one that I mentioned earlier, that of this QED in 1 + 1 dimensions, there was no particle production at any time. I mean, if you choose that particular configuration as your initial condition, then that's it. Another example is if I have a soliton, let's say a kink in 1 + 1 dimensions, I know a sitting kink will not produce any particles. But now, even if it's interacting with other fields, sitting kink will just sit there, and I can boost it. And if I boost it, then I know once again that it's not going to produce any particles. So even though the background is time independent, there is no particle production. So those cases correspond to the situation where Z is not invertible. And that actually has to do with symmetries of the system, that there should be some symmetry, and the time dependence, like for example, in the soliton case, there should be some translational, there's translational symmetry, and all the time dependence is in that translational degree of freedom. So it is just translating. In that case, this argument fails because Z is not invertible, and then you can have an always an unexciting situation. So so maybe that's what I say over here. So yes, so basically that's what this says, is that there should be some symmetries, and the background should have a zero mode. And as I said, if you have a boosted soliton, also a PP wave, for example, they are known not to produce quantum excitations, and that's because of the symmetries. So I guess there's a lesson that an always unexciting background should have symmetries that lead to zero modes of the quantum excitations. So maybe this is also a lesson for the non-Abelian flux tubes we were talking about, that maybe they should have some symmetries. And maybe the time dependence is all in those symmetries. This example, the QED 1+1 example, is slightly different, and sort of goes back to Marcus's question about the picture in fermions. So the Lagrangian, in terms of fermions, depends on this gauge function, and you can work in temporal gauge, and then A will have some time dependence. But the correspondence we had with the classical and the quantum dynamics only applies to bosons. So we can't really work with fermionic excitations. But once we come to the bosonized Lagrangian, then the coupling is over here to the epsilon f, which is the electric field. And this is time independent. So it really, so really there's no time dependence and there's no particle production in this case. So you can have an always unexciting electric field in this case. All right, that kind of brings me to the end. So unexciting classical backgrounds are protected from quantum decay. And for the simple harmonic oscillator, there's a huge space of such unexciting backgrounds. Homogeneous field backgrounds can be unexciting for some quantum field modes, but not for all modes. And then even for inhomogeneous backgrounds, you can construct some, you can find unexciting backgrounds, but whether they are physical depends on what system you're considering. And yeah, this is an open question. The always unexciting backgrounds require symmetries of the background and the existence of corresponding zero modes of the quantum excitations. So, thank you. Yeah, if you have any questions, I should say, by the way, that I've been thinking about the non-Abelian case a little more, and if you ask me, I can try and give you what I've learned so far.
Sorry, maybe I missed it, but you say you have a huge space of unexciting backgrounds for the harmonic oscillator, but including always, not including always unexciting, I would guess, or?
Yeah, in the case of the simple harmonic oscillator, it becomes kind of trivial because, let's see, if I just, sorry, maybe I can just go here. So in that case, this Z is just a complex number. So then I just, over here, I just get a product, a little omega prime Z is 0. And so it's just a product. And so I can always divide by Z.
Yeah, so that,
yeah.
Right.
So there is no question. Here, because there are many degrees of freedom, you can have time dependence in some degrees of freedom for which Z, well, there's a zero mode, so the whole thing sort of becomes undefined in some way.
Another question is, did you consider rotations? I mean, it's very intuitive that somehow a translation should not give you radiation, right? I mean, this is kind of, this is a nice way to see why radiation cares about acceleration, actually, right? So, but on the other hand, somehow rotations, intuitively, you would think that generically, even though they're a symmetry, they would generically at least give you radiation. Like if you had scalars or something, maybe you need to have scalars, or I don't know. Have you thought about that at all?
Actually, I haven't, and that's a good point. I've been sort of that's a very good point. I haven't thought about it, but I've been thinking about for non-Abelian theories, there's a sort of a rotor degree of freedom. So it's not really rotations in physical space, but in field space. And there, those backgrounds are unexciting. And actually that sort of applies to non-Abelian gauge theories, where you can have, well, you can have rotation between W1, if you're W1, W2, W3 are SU2 gauge fields, then you can have rotations in W1 and W2, and that will not.
These are gauge rotations.
Yeah, gauge.
Rotations in gauge space.
Yes. Yeah.
Mhm.
But yeah, I haven't thought about physical space. That would be interesting.
Okay. Thanks. Yeah.
Can I ask a question? So normally, if we have some sort of, in cosmological applications, for example, you're thinking about, producing particles by discharging some background field or something like that. And it's been, very popular to recently. And by that, I mean some number of years, actually, to kind of, excite all kinds of things by some sort of, preheating, like a type setup where you have something like parametric resonance and whatnot. And usually the idea there, as I understand it, is that you have basically some sort of initial condition for the field where the field is rolling, it's mixing with some other field and making its parameters depend on the wave. And so, eventually you get into this resonance band and you make lots of. So is what you're saying, I mean, now there, usually the assumption is that the eventual attractor for this type of evolution is that the field settles down in its, highly symmetric vacuum, and then these processes completely stop. And are you, for example, can I interpret what you're saying is that maybe there is other attractors which are not quite as symmetric or vacuum or something like that, that you could end up evolving to, even if they were metastable?
I'm not sure the attractors but I guess.
I mean, if you have some sort of equilibrium-like configuration where you're not making particles and your field is not in the vacuum, I'm just curious.
Well, so the obvious example is this scalar field rolling down the inflaton and then producing particles. But I guess you could make it roll in such a way that it doesn't produce any particles.
So right. I guess that I understand that that's what you're saying, but would then the system naturally evolve to this configuration as opposed to just roll to the minimum and stop there?
And that's a good question.
I'm very curious because in some sense maybe you have usually we think about a quote unquote slow roll as a way of forming some sort of a
but wait,
long-lived configuration that does interesting things. Maybe this is anyway. I'm just curious.
No, but I think maybe this is the answer, is that you can make it roll so that a particular mode is not excited, but you can't make it roll so that no mode is.
I see. Okay, I understand. Sure.
There'll always be some, yeah. Yeah.
So if you were doing something like quantum mechanics, you're saying problem is field theory. In field theory, if I have a full range, a dense spectrum of degrees of freedom and whatnot, somebody will always be excited.
Right.
But if I had some sort of a gap spectrum or few degrees of freedom or something like that, then I might get away with it.
Right.
Okay.
Right. Yeah. Okay. Yeah, by the way, there have been this question of backgrounds that are protected against quantum decay have come up in the past. as well. A paper by Brown and Weisberger in the context of the Schwinger pair production. So people have thought about it, but I don't think I've never heard of a closed sort of description. What would it take for things to be protected? But I guess one could also imagine a situation where you want to take a simple harmonic oscillator and change some electric field backgrounds or magnetic field backgrounds, but you don't want to excite it as you're doing it. And then maybe something like this is useful.
Any more questions, guys? Comments? All right, I guess in that case, we can thank Tanmay and
Well, this was a pleasure.
likewise.
Great to see you. Thank you,
Yeah.
Tanmay.
And I'm happy to answer any questions. If you have any, you can email me. Okay.
Thank you.
Bye.
Thanks a
Nice-
lot.
Bye-bye.
Thank you.
Bye.